We have 3 more papers. The title of the paper to be presented now is Application of CFD for Investigating Effectiveness of Energy Saving Devices, something which has now become very important with the EEXI and the CII measures that have been put in place by IMO. This particular paper is authored by 5 authors from Indian Register of Shipping, Mumbai, Research and Development Division. The authors are Himanshu Uppal, Dr. Joseph Prabhu, Shanmukh Srinivas, J. Ramkumar, and Mr. S. Dhavilkar. We have in the audience today 2 of the authors, Dr. Joseph Prabhu, who will make the presentation, and Mr. J. Ramkumar, who will take the question answers at a later stage. Now, Joseph Prabhu is a student from IIT Kharagpur. He holds a degree in BE in Civil Engineering and an ME in Structural Engineering, and then a PhD under Professor Vishwanath Nagarajan from IIT Kharagpur. He is right now looking after the Department of Hydrodynamics and Multiphysics in the Research and Development Division of Indian Register of Shipping, and he is into CFD along with the computation using OpenFOAM software. So I request Dr. Joseph Prabhu to please come up and make his presentation, and let us again a request to stick to the time. Thank you.
Thank you, sir. Yes, good evening to all. It's a great privilege to deliver a talk under my Professor Shah. So I thank Dostas for giving such an opportunity. So actually yesterday few speakers have given few glimpses about the EXA and EDA. That almost around 30,000 vessels need to be undergo this EXA criteria need to be implemented. So in order to that, MBPC have given set of guidelines how we need to calculate this EXA compliance guidelines. So we need to either we need to have a sea trials supported with the model test of the parent hull. Else, in case many old ships might not have the model test of the parent hull. So in that case, we can go for CFD calibrated with the sea trials of the comparable ships. So in case the comparable ship, the definitions means it will be either the ship should be of the same type, and the sizes like LBP, CB, the criteria should be within the 10% variations. And else we can, if we are unable to find the similar ships of the same length or that, then we need to go a set of comparable ships. Almost 10 ships we need to compare, then we need to can attain this EXA values. So for that purpose, we need to evaluate the speed power curve of the hull characteristics. So in failing to achieve this EXA value, so they need to opt for power reductions. So that will come up with the loss to the ship owners. So in that case, in order to improve the EXA compliance, we can add some energy saving devices or some energy saving technology to improve the speed power curve, and we can maintain the same power retention. So in this paper, I will be detailedly discussing on how we can put on ESD and we can calculate the effectiveness of the ESD, how it will be improve the performance, and how we can maintain this EXA value. So this it will take to a extent up to, if they are near to we are around 5 to 10% we are away from the EXA criteria, then we can go for these options and we can achieve this. So my next slide, yeah. So this is my content of my presentation. So first I will be talk about the energy saving devices what are currently available in the market and frequently used things. Then I will be talking something about the computational fluid dynamics and the methodology followed. Then I'll be doing the resistance barrel resistance calculations. Then I will be doing open water characteristics with and without PBCF. So in this paper, I will be using energy saving devices as the PBCF. And after that, once the popular open water characteristics available to me, I will go for set propulsion, and finally we can conclude it. Okay, fine. So this is the few energy saving devices listed here. So this first one is Grimvane wheels. So that will improve the efficiency up to 2 to 3%. So it will make use of the rotational fed from the propeller, and it will give some additional thrust. And the wake equalizing that will improve the flow to the propeller. And similarly, the rudder bulb that will make use of the vortex shed from the hub. And the pre-vertical stator and maybe stack are similar. That will both are work on the same principle that will improve the flow to the propeller. So our main concentration today is the propeller boss cap fin. So that we used JVC propeller. In that we fitted this PVCF fins, and we done the CFD analysis, and we can see how it has improved the propeller efficiency. So before going into this, let's basic comparisons between EFD and CFD. So the steps involved in CFD, we all know about it's the time consumption and cost expensive. So CFD we can hardly within 2 to 3 years we can get a resistance test, and open water self propulsion can be done maximum up to 4 to 5 hours if based on our computer resources available. So still CFD has more advantages, like we can get the entire the parameters over the entire hull, and the various parameters can be measured throughout the hull. But in experiment, it should be, we can get it particular where we place the sensors and where the load cells. Based on that, we will get limited to data. But still, we need to, using CFD, we should be careful how to using the numerical model, which model we need to be used, and finally we need to validate our results with the model test experimental results available. Then we need to proceed. So the basic structure of fluid dynamics. So in our case, our problem is the multi-phase flow problem. So air and water interface. So finally the governing equations we need to solve using the RANS model. So we need to, as per MPPC circulate guidelines, we need to use the two equation models like K omega, K epsilon, or K omega SSTs. So each model has its own advantages, and these three models what I mentioned here are most commonly used in the computational domain. So that K omega model, that will be very good in capturing the laminar near the boundary layer. It will be good in capturing the boundary layer effect. And the K epsilon model is good in capturing the turbulence flow around the hull. And making the combination of these two, actually the K omega SST model is developed. It will be near the boundary layer, it will be solving K omega, and the turbulence away from the boundary layer, it will be using K epsilon. So that will be the most efficiently used for the resistant production and self-propulsion characteristics. We will be using K omega SST model. So then we'll be discretizing the domain. So finally we'll left with a set of PDAs. So we need to solve it by making a domain, and we need to make a grid and refinement study. That is the important one. So that will be increase our accuracy and reduce the computational time. Then how we'll solve these models? We can use commercially available softwares like StarCCM, ANSYS Fluent, etc. And we can use some open source available like OpenFOAM. So we will be using both StarCCM and OpenFOAM for the computation of these simulations. And then we'll do the post-processing, and we can draw out the results, and we can compare with our model tests anything available, and we can calibrate it. Now, in this study, we have taken JBC hull as our benchmark vessel. So we made the computational domain as per ITTC guidelines followed for the CFD. So forward we have taken 2.5 L, and aft we have taken 2.5 L, and depth we get is 2 L. and above the draft line we are taken as 1L, and along the sides it will be 2L, and we are given the inlet boundary condition as velocity and pressure outlet. Then side, bottom and top are the velocity inlet. The hull particulars and details are given here. So the reason for the lesson, this is the data as model test is available, so we can compare easily with our CFD results. So refinement zones is an important thing to get the convergence and the quicker solutions. So if you wherever fine grid is required, we can go with fine, and it is not required throughout the domain. So we can reduce the cell count and our computational expense will be reduced. So some refinement zones like bow refinement is required in order to capture the wave part, and the prism layer need to be made around the hull in order to capture the boundary layer. So that we can see from the bow refinement, and the stern pattern also refined very fine in order to capture the wake part. Then in the plan view, we can see these things should be in the Kelvin wake pattern as in order to catch the wave forces created by the waves. And this refinement should be made according to the ITTC guidelines and according to our hull shapes. Then after doing this, we need to go for a grid convergence study and time independent study. This is the most crucial part. We need to, if you go for more finer also, sometime our solution will not converge. So based on our boundary Y plus value, and that criteria comes into play. So if you see, we done by L by 38, L by 50. L by 38 is quite coarse, and L by 50, and again we are moving towards finer. So we find L by 50 is the optimized size, we can go for it. And we similarly for time step, we are while integrating the PDEs, we need to march with the time step. So L by 100 we are optimized as the time step. So these two time steps and the grid dimensions we are used for the upcoming simulations. So you can see the resistance what we obtained here. So the final solution is shown in the right hand part. Left hand side we can see how the solution starts and how finally we'll get a converged solution. So we run the simulation at 1.17 meter per second, and with a course of with the grid dimensions of 1.7 million. So the resistance value, we are little away from the experiments. It's 4.5% error. That is quite tolerable as per the ITTC norms. So in order to do the simulations, it took around 2 hours. Based on our computer research, we used 100 core simulations. Then once we are done with the resistance, we'll move to the propeller, open water, in order to learn the propeller characteristics. So we made a circular domain as propeller is rotating radially. So the domain is prepared 5D forward and 10D behind in order to capture the wake, and the 3D in the radial directions. And similar patternly, we need to make a grid refinement near the propeller. We need a very fine grid to capture the turbulence. And we got various stages of refinements is done here. 2 3 stages refinements is done here. And the propeller characteristics, you can get it from this table. Okay, fine. So then we can do this propeller open water in 2 techniques, moving reference frame and rigid body motions. So in moving reference frame, we will be making the propeller fixed and we will be rotating the fluid particles around it. And in RBM, we will actually rotate the propeller and its actual physics. So, but what is the advantages of MRF? It will be giving a quicker solutions than the RBM, as in RBM, in order to regularize the fold, minimum 5 rotation of the propeller rotation is required. That will take a huge time. So if you use MRF, it will give a good, quicker solution. So similarly, we compared with it, MRF and RBM, which one is better. So almost it is following in the same phase. So we used MRF here in order to get the open water characteristics. So here you can see the right one are with PBCF. So left one is the without PBCF. So we can see while fitting the PBCF, we can see the intensity of the right part. We can see the intensity of vortex is minimal compared to the left hand one that is without PBCF. So that is the energy gain we can get in using the PBCF. So the vortex loss of energy in the vortex can be gained in the form of and we can get a better efficiency. So almost 2.3% we got a better efficiency in this using this PBCF. Then once this is done, we have gone for, once we obtain this self-propelled, we can from using the open water, we can get the self-propelled RPS. So then we can go for the self-propulsion. So here we can have three techniques. We can use virtual disk method, that is most quicker one. Just form the propeller domain as a virtual disk and give the input parameters of the open water characteristics of the propeller, and we're ready to go. And we can similarly, we can use moving reference frame. As I mentioned earlier, we can rotate, we can keep the propeller fixed and we can rotate the fluid particles around it and we can achieve that. Similarly, that third one is the rigid body motion. There we can actually rotating the propeller, other things remains normal, and the RBM, as I said, it will take a more computationally most expensive than MRF. So finally I am coming to where I started, that MPPC regulation, how we can achieve this, attain this power retainment. So we can see the dotted lines are without the power speed per car without PBCF, and the bottom one, thicker ones are with PBCF. So in the left graph, you can see the power gain. In the green portion is the power gain we have obtained using the PBCF. And in terms of VREF, we will see the velocity gain. If you are moving, we are maintaining it in the same power, but we can move at higher speeds. So these are my key conclusions. So we can use the MRF for open water, that is computationally less cost expensive and fast. And rigid body motion, we need to be useful for high speed where turbulence is heavy. The high speed vessels, we can go with rigid body motion. Then self-propulsions based on virtual disk always gives it's a quicker solution, but it will be estimate higher, that we have learned from our previous studies. But we can relay a little bit as per the guidelines given by the ITTC. Then for ESD such as PBCF, open water simulations, we no need to do the self-propulsion with PBCF. We can, once we done the comparison in open water with and without PBCF, we can get the efficiency improvement, and from there we can get the overall efficiency improved. Then we can combine the ESDs like PBCF, vacuous duct, or PBCF with MUS duct. That combined effect can be also studied in the future. So almost, if you use these ESDs, we can able to achieve maximum at the max. We can achieve 5 to 6% of improvement. That will that we can go close to if we are very close to the EXA, then we can look into these options. Okay, these are the few references. Thank you.
Thanks a lot, Dr. Prabhu, for not only giving a very excellent presentation, but also finishing right dot on time. Both the first paper of this particular session 5 and and one given by Professor Anandasubramaniam and Dr. Joseph Prabhu, I hope the audience realizes the difficulty one faces while doing CFD simulations. People approach us, could you do a CFD simulation? And they think that within a day or two we could give them the results. Getting the model ready itself is a very difficult task, and some of them were highlighted by both the authors in this regard. So thank you once again, Dr. Prabhu, for an excellent presentation, and I wish the audience give him a big round of applause.